and let us start. So that is now the volcanology class ES303. And what we are doing here, we are talking about volcanoes. So here in the South Pacific, it is a very strong area or a very famous area of active volcanism. Most of the Fiji Islands, let us say we have about 320 islands, and of these 320 islands, maybe 300 made up of volcanic origin. So and here in Viti level we have different volcanic rock sites. Most of the rock types here are basalts, andesites, schorschenites. I will tell you more about later. So and then you have also the counterparts here in Viti level, you know this. We have, when we are talking about volcanic rocks, we are usually talking about explosivas. Explosivas, these are rocks which are erupting at the Earth's surface. The counterparts to these explosivas, they are then the intrusivas. So in the intrusivas, as I showed you yesterday in the ES301, these are magmatic rocks which become stuck below the Earth's surface like granites. So for those of you who did the ES106 field trip, you saw some of these extra intrusivas. These are the condolites here, these are the more acid rocks of granitic composition. And then we have also the gabbros, and the gabbros are the counterparts from the basalts. So that means this gabbros has the same chemical composition as a basalt, but the basalt was cooled down close to the Earth's surface. Therefore, it is very fine-grained because it cooled down very fast. Whereas the intrusivas, the gabbros, which is typical for oceanic crust, was cooled down below the Earth's surface. By telling this, we can classify these volcanic rocks. So that means, first of all, we can classify them petrographically. So in the petrographical classification, that is a classification which you can observe in your hand specimen, yeah? You are going to the field, you are sampling some rocks, and then you can tell me immediately if this rock, for example, is black, yeah? So that is one of the first things you are using the color, yeah? That is the first thing what you can observe with your naked eye. If this rock has some, or it has a certain color, yeah? Most of these basalts here, or not only most of these basalts, all of these basalts are black, yeah? And most of you saw them a lot of time during the field trips. So maybe we have here something nice. So that is such a very gas-rich basalt, for example. So here we have an obsidian, and this obsidian is actually SiO2, and that cooled down very fast, and you can't see any gas bubbles inside, so that means the smell which produce this obsidian was a melt which is very poor on gas or volatiles. Yeah? We are talking here in petrology always about volatiles. That is because it's always a mixture between water and CO2, and then you have a little bit methane inside. And a little bit nitrogen. So, but anyway, we have here the petrographical classification, and therefore this petrographical classification is based on observation. So in this observation, of course, the first is the color, the next thing is the texture, yeah? For example, do you have such gas bubbles inside or not, yeah? The texture. So what do we have else? The structure. The composition. So if we are doing a petrographical description and telling or make some estimation about the composition, then we can just check by looking at the hand specimen or by making a scene section and checking it beneath the microscope or on a microscopic table. Then you can make some assumptions which minerals are inside. Yeah? So some of these, I mean here, in this one you will not observe any mineral inside because it is in fine grain. Yeah? So, but some of them have xenocrysts, for example. I will tell you later what a xenocryst is. That means you have some minerals inside the very fine-grained matrix. So, and then you can make some observations and telling me what minerals are inside. And for example, those of yours who visited last semester with me Polo Island, there you saw a lot of basalts, yeah, more than you like. And in these basalts you could see some xenocrysts inside. So, and these xenocrysts have been an orgite, yeah, you remember. So, and the orgite is a pyroxene which is formed at very high temperatures, and these orgite crystals were up to 1 centimeter in diameter, could that be, yeah? So, and what other xenocrysts you could see in these andesites? White one was the plagioclase, yeah? So, in the plagioclase, that is a feldspar and can be described by using these two end members. That is the amortite, which is the calcium-rich end member, and the albite, which is the sodium-rich end member. So, and if you are then looking for such a magma chamber, and then you know that the orgite is crystallizing very early in the fractionation or crystallization sequence and has a high density, yeah? Because such an orgite is a clinopyroxene CPX. So, and that you have then the end members dioxide, calcium, magnesium, Si2O6. Then you have the Hedenwaldite, that is then the calcium iron, Si2O6. So, and then you have the enstatite, which is an Mg. I'm writing it always down in this way because then it is easier if you are splitting this mineral chemical formula in tetraeder spaces and octaeder spaces. We have done this last semester. So, and then you have the ferrosilite, you know this by now as well. There you have iron, Si2O6. So, and then you have the jadate. So in the Jade you have here a sodium AlSi2O6, and you have the acrid. Then you have here sodium, here you have iron 3 plus Si2O6. So and then you are making a mixture from all these 6 end members and putting also a little bit titanium inside. Then you have the orchide. Yeah? We will talk about the orchide later more in detail. But anyway, this orchide has a higher density compared to the surrounding melt, and therefore it will sink down to the bottom of the magma chamber. So and here on the other side I have just drawn yesterday such a magma chamber for our applied geology class. So that means this orchide crystal will crystallize here and will sink down to the magma chamber, yeah? Because of the higher density. That is just differentiation, yeah? So whereas if we have a plagioclase, and you can see here we have some elements which are less heavy, and that means less dense. So and then your plagioclase will crystallize here, and it will floating up to the top of the magma chamber, because the plagioclase has a lower density compared to the surrounding belt. So and some other minerals like the olivine is just sitting here and floating. So and all this description fall under the petrographical classification, yeah? The occurrence, but not any genetic relationships. So what means this now? This is another thing which makes it the main topic from this class. We are classifying all the magmatic or igneous rocks, and they are mainly the extrusivas according to their genetic relationships. So, and you know by now, I mean that you know maybe since your earliest childhood, that different igneous rocks are formed in certain geotectonic settings. So you have, for example, the Middle Ocean Ridge, yeah? So in the biggest Middle Ocean Ridge system is South Middle Ocean Ridge system in the North and in the South Atlantic. So if you are looking at the world map, then you can easily identify the Middle Ocean Ridge between, or which separates North America from Europe and South America from Africa. Yeah? It is a very long Middle Ocean Ridge system. So in these Middle Ocean ridges, you are forming certain types of basalts. Yeah? So they have a certain chemical composition. We are saying that these basalts at the Middle Ocean ridges are depleted. Yeah? So what I'm always talking, you can write down or not, but important is this stuff which I'm putting on the board. Yeah? And then you can later on watch the movies. So because about this genetic description, we will talk later on much more in detail. So here in Fiji, for example, we do not have a Middle Ocean ridge, but we have a subduction zone, yeah? So we have actually two. One is slipping from the east to the west, and the other one is slipping from the west to the east. So in such a subduction zone, you are forming genetically different basalts compared from south to the ocean, Middle Ocean ridge. So So they are chemically different. Yeah? So, but if you are taking the hand specimen or watching the hand specimen, then you cannot, only by telling me from your observations, you cannot tell me if this is an ocean island basalt, like we are sampling it here, or if this is a middle ocean ridge basalt. Yeah? Therefore, you need a chemical analysis. So, and some other basalts are then, for example, the continental flat basalts. Yeah, we will talk about the continental flat basalts in South Africa. There's the Bushveld complex. It is actually a very huge layered intrusion. Then we have volcanic rocks which are related to orogenic processes. If we are talking about an orogenic process, then we are talking, for example, about a collision process. So that can be a continent-continent collision, or it can be a oceanic crust continent collision, like we can see this in the Andes in South America, or it can be a collision between two oceanic crusts. So like it is here or in Japan, yeah? So, and then we will also talk about some specific things like the kimberlites, for example, yeah? So then the next thing is we have then the petrological classification. So what means this now? If we are talking about petrology, then we are talking about the process which leads to the formation of different rocks. So these are then rock forming processes. So, and if we are talking about rock forming processes, then we are talking about anorganic chemistry. So you should know by now mineralogy and petrology that it's nothing else as anorganic chemistry. So, and these rocks were formed from a different parental melt. So, and that means we have somewhere a melt or a magma, and this melt or magma has also somewhere a source, has a certain chemistry, and according to their chemistry, we can then form a certain type of rocks, which consist of a certain type of minerals. Yeah, that's the way how it is. So, in these rock forming processes, then are also strongly controlled by the pressure and the temperature. So there are some melts which are formed at higher temperatures, and some other melts are formed at some, let us say, certain rocks are formed at higher temperature coming from a certain melt, and other rocks formed at a lower temperature formed from a certain melt. So others are intruding more close to the surface, others becoming more or less stuck in the Earth's upper and lower crust, and others are extrusiva and become cooled down at the Earth's surface or very close to the Earth's surface. So then we have here rock forming processes, we have the development of a magma. There we are talking then about fractionation processes, assimilation processes, contamination processes, differentiation processes, magma mixing and all this stuff, which are own chapters. So then we have this, then the origin of the melt. I just told you some of them are formed at the middle ocean ridges, some of them are formed at the subduction zone, and some of them they are coming actually from the core mantle boundary. There I have then also some movies. So in this meteorological classification, consistent of the mineralogy. So when the mineralogy, as the name says, deals about minerals and the chemical composition of these minerals and under which pressure and temperature conditions and other conditions like oxygen, fugacity and so on, these minerals has been formed. So then we have the petrology. We have the petrography, we have the geochemistry. So what means now the geochemistry? All rock-forming minerals, they are mostly formed by elements like iron, magnesium, calcium, silica. Silica very important, yeah, because it is very important to describe the silicate structure, and all rock-forming minerals on this planet, they are actually silicates, yeah. You have the autosilicates, ring silicates, chain silicates, double chain silicates. We did all this last semester. So then you have sodium, aluminium, iron and iron 3 plus, potassium, and all these elements are the elements where we can build up our minerals. So, but then we have still the light rare earth elements, the heavy rare earth elements, the high field strength elements, which we are calling then altogether the incompatible elements and the rare earth elements. So, and these are then elements like strontium, rubidium, barium, cesium, all these elements which